Hello, I would like to introduce my research poster to you. My poster's name is 3D Thin Acceleration using block circulant matrix in frequency domain. Recently, 3D Thin have achieved great success in applications such as video analysis, 3D geometric data, and 3D medical image diagnosis, as shown in the figure below. However, the huge storage and computational overhead of 3D Thin hinder their deployment on edge devices. To tackle this challenge, in this work, we propose 3D F-Circuit CNN, an aggressive hardware co-design approach to realize efficient 3D Thin acceleration. First, at the aggressive level, we apply block circulant matrix to compress 3D CNN and further accelerate the computation with FFT. We also introduce several 3D CNN operators in the frequency domain to eliminate the frequent special frequency domain switching overhead caused by FFT and RFFT. Second, at the hardware level, we design an FPGA-based dedicated hardware architecture to accelerate 3D CNN efficiently. Before we introduce optimization at the algorithm level, let's introduce some basic knowledge of the circulant matrix. Here is a definition of the circulant matrix. A K by K matrix is a circulant matrix if and only if each column vector is a circulant reformat of the other column vectors, as shown in Figure A. Circulant matrix has many interesting properties. The most important property is that a circulant matrix only needs k elements to represent. Thus, therefore, a bigger OK storage complexity reduction can be achieved. Besides, the multiplication of the circulant matrix W and the vector X can be accelerated by FFT, as shown in the equation below. Where small w is the vector formed by the elements of the first color of big W. However, not all matrices are square. For an m by n matrix W, we first partition it into p by q blocks Wij, where p equals m divided by k, q equals n divided by k, and if each block is a k by k circulant matrix, then we call W a block circulant matrix, and K is the corresponding block size, as shown in Figure B. We then describe how to compress a 3D CNN using circulant matrix. First, for the fully connected layer, since the weight W is an m by n matrix, so we directly constrain W to be a block circulant matrix to compress the fully connected layer. As for the 3D convolutional layers, first, we consider the n by n by k by k by k weight tensor W as k cubic n by n matrix, and then we constrain each matrix to be a block circulant matrix, as shown in Figure A. According to the property of the circulant matrix, we only need to store the first color of each circulant matrix. Thus, the compressed widths have the form shown in Figure B. However, through block circulant matrix compression, and FFT acceleration, the data flow of the convolutional and fully connected layer becomes FFT, element-wise multiplication, and IFFT, which leads to frequent special frequency domain switching overhead in the forward propagation process. For simplicity, we omit BN and pool operation. However, FFT and IFFT is computationally intensive, and designing an FFT and IFFT module will consume additional hardware resources. To address this problem, we introduce 3D CNN layers in the frequency domain, including C-ReLU, CBN, and CMaxPro, which apply ReLU, BN, and MaxPro on the real and imaginary parts, respectively. Then the forward propagation process becomes element-wise multiplication, C-ReLU, element-wise multiplication, and C-ReLU. It can be seen that by introducing activation, bench normalization, and pooling layers in the frequency domain, we further eliminate the overhead of FFT and IFFT, and realize the full frequency domain calculation, which is also the main difference between this paper and work 4. Based on the algorithm optimization, we further designed an FPGA-based 3D CNN accelerator. Our accelerator's overall hardware architecture is shown in the following figure. As can be seen from the figure, our accelerator mainly consists of 3 parts. They are on-chip buffers, a processing element area, and a post-processing unit. Firstly, on-chip buffers contain input future buffers, wait buffers, and output future buffers. They are all double buffered to cover the data transmission time. Secondly, the processing element is the core computing component, which contains several complex multiply accumulate chains. Besides, Gaussian complex multiplication is used, thereby the cost of one complex multiplication is reduced from 4 real multiplications to 3 real multiplications. Thirdly, the post-processing unit includes complex BN, complex ReLU, and complex pool units, which are responsible for computing the batch normalization layers, activation layers, and pooling layers in the frequency domain, respectively. Finally, we evaluated our proposed approach. We implement C3D on the Xilinx CCU102 FPGA board, and the UCF101 dataset is used. We use block circulant matrix with a block size of 8 to compress C3D, and replace ReLU, BN, and MaxPro with C-ReLU, CBN, and CMaxPro. The experimental results can be divided into 2 parts. First, the training results show that our approach can lead to a 4.8 reduction in flops and a 7.9 reduction in memory, while the accuracy loss is within an acceptable range, about 1.25%. Second, as can be seen in the table below, our accelerator achieves the highest throughput and DSP efficiency, and demonstrate 1.99 by 16.68 and 2.53 by 16.18 improvement compared to previous works, respectively. These are the reference literature used in this presentation. Finally, thank you for your listening.